In this talk, I now want to describe the main results, which is to define the first non-trivial examples of deformed G2 instantons. So to define the setup, I'm going to return to our model example of the 7-sphere. So let's recall that we have this Hopf vibration of the 7-sphere over the 4-sphere, fibered by 3 spheres, and that we have a 3-form, which I called phi ts, that induces the round metric GTS. And this 3-form is a non-degenerate 3-form, therefore a G2 structure. Now, we know that S3, of course, is the same thing as the group SU2. Hence, it's parallelizable. And we have 3 left invariant 1-forms on S3, which are independent. So they form a coframe. Let's call them eta1, eta2, and eta3. And on S4, we have 3 orthogonal self-dual 2-forms with the same length, 2, omega1, omega2, and omega3. So we already saw the same sort of 2-forms in the case of R4. We saw them in the previous talk. Now, out of this data, we can build ourselves 2 one-parameter families of G2 structures. And we have a continuous parameter T positive and a discrete parameter, which we'll call plus and minus, as follows. So it's not too important what the formula says, but it says that we get 2 families of G2 structures, phi T plus and phi T minus for any T positive. So let's make some observations about this family. The first key observation is that phi T plus and phi T minus both induce the same metric. In fact, it's the metric GT that we saw before when I was talking about the canonical variation. In particular, phi T plus and phi T minus are isometric G2 structures. So this is what it means to be an isometric G2 structure, or 2 G2 structures to be isometric, is that they define the same metric. We also see that all of these G2 structures, they're co-closed. So the star here, remember the star depends on phi T plus minus itself, but all of these things are co-closed. That's important because it means that we can define deformed G2 instantons for these G2 structures. So we can ask, when are these phi T plus and minus nearly parallel? And that's exactly 2 cases. The first case is the one we saw before, phi Ts. That's when T equals 1 and we take the minus sign in this equation. But the other possibility is that we have T is 1 over root 5, because that will define, as we know, an Einstein metric here, but we have to take the plus sign now in order to get the right nearly parallel condition. So we call this phi NP. And so we have 2 very special G2 structures in this family, phi 1 minus and phi 1 over root 5 plus, which we call phi Ts and phi NP respectively. Now we notice that this phi NP will define the other Einstein metric on the 7-sphere in the canonical variation, which is often called the squashed Einstein metric, because we have squashed the fibers in the Hopf vibration relative to the usual round metric case. So this is exactly what we need in the case of the 7-sphere, but we can do things more generally as follows. So we want to look at what are called 3-Sasakian 7-manifolds. So the definition is that a Riemannian 7-manifold is 3 Sasakian if and only if, when I look at the cone on that 3 Sasakian 7 manifold, so that's now an 8 manifold, and I define the cone metric so that our 3 Sasakian 7 manifold is the unit sphere in this cone, then that cone is hyperkähler, which is to say that the holonomy of the cone metric is contained in sp2, so the compact symplectic group sp2. And we notice that this just generalizes the case of the 7 sphere, right? Because in that case, the cone is just Euclidean space and its holonomy is trivial, so it's clearly hyperkähler. Now, you may ask, well, that's one case. Are there any other 3 Sasakian 7 manifolds? In fact, there are infinitely many. So that's nice, because that means that we've got lots of places to try to find and build DG2 instantons. And they all have the following form, that they are fibrations over some anti-self-dual Einstein 4 manifold by 3 manifolds which are finite quotients of SU2. And what that means is that we can play exactly the same game as we did on the previous slide. We can choose a left invariant coframe, eta1, eta2, eta3 on V. We can choose self-dual 2 forms, which are orthogonal to each other and all the same length on Z, and then define our phi t plus and minus, which induces the metrics, which we can call gt, which are just t squared times the metric on V, plus the metric on Z. So here, this is just the left invariant metric, or bi-invariant metric, in fact, on SU2 mod gamma. Now, given this, we can ask, do any of the other properties persist from the previous slide? And the answer is yes, that if we take phi 1 minus, it's a nearly parallel G2 structure, which we'll call phi ts, because it induces the original 3 Sasakian metric GTS. And now you can see why I bothered to use this TS superscript along in these talks, because it stands for 3 Sasakian. And similarly, if you take phi 1 over root 5 plus, that's going to be nearly parallel, so we'll call it phi NP, and it induces a metric which we'll call GNP, which is another Einstein metric on a 3 Sasakian 7 manifold. So just like on the 7 sphere, where we have a standard Einstein metric, which is the round metric, the 3 Sasakian metric, you can also find another one in this one parameter family, which is a squashed Einstein metric. And why do we call this one particularly nearly parallel? Because this one is as well. Well, because now, if you look at the cone metric, in this case, it has holonomy equal to spin 7. So that's a larger group than sp2. So this is a what's often called strictly nearly parallel structure. So it is not the same as the 3 Sasakian case where the holonomy is contained in sp2. Here the holonomy is actually all of spin 7. And as I said, there are infinitely many 3 Sasakian 7 manifolds, but an important example that I'll mention in the following talks is the Arlaf-Wallach space SU3 times SU2 quotiented out by U1 times SU2. Just to show that here is an explicit example of a 3 Sasakian 7 manifold that isn't the 7 sphere. So now we know the setting in which we want to search for TG2 instantons. Here is our two one-parameter families of G2 structures. So here is the result, the main result of this sequence of talks. It says if you have the setup in the previous slide, so you have a 3 Sasakian 7 manifold, and you have your G2 structures phi t plus or minus, inducing this one parameter family of metrics GT, and you choose a coordinate A on R3, and you define a connection, capital A, on the trivial line bundle over X7. So we're going to write it as I times A1 e to 1 plus A2 e to 2 plus A3 e to 3, where we recall that the etas are the left invariant coframe on the three-dimensional fibers of X7 thought as a fibration over a four-dimensional AST Einstein four-manifold. And there's one last piece of data, which is I'm going to define the size of A, just the Euclidean norm of A. I'm going to call that R, and I can think of that as the distance to the trivial connection, because when R equals 0, A equals 0, that means I'm taking the trivial connection on the trivial line bundle. And so the question is, when is this connection a DG2 instanton? So that's the theorem that I'm going to present now, due to myself and Gonzalo Aravera, that says that A is a DG2 instanton for these G2 structures if and only if the following is true. So I'm going to draw it as a picture. So here is the size of A, which we called R, and here's the parameter T. Then if I take the G2 structures phi T plus, then for all T, I have the trivial connection. That's a DG2 instanton in a trivial way. But then I also have a non-trivial family, which is actually an S2 family of DG2 instantons that exists for all T's strictly between 0 and 1 over root 2. So there we are. We have some new examples of DG2 instantons. So what about phi T minus? Well, in that case, the picture's slightly different. Now we again have the trivial connection, of course, which is just a point. We also have exactly the same curve here, but now rather than defining an S2, it defines just 2 points, so just 2 examples of DG2 instantons. Again, between T is 0 and 1 over root 2. But then we have an additional feature. We have an S1 family of DG2 instantons defined for all positive T. And so we see that all in all, we get a whole bunch of new DG2 instantons for any 3-Sasakian 7 manifold and for a variety of different G2 structures on it. And just to remind you, where does the special G2 structures live? So in particular, the 3-Sasakian G2 structure, well, that's here. That was phi 1 minus. And so that's here, and it only has either the trivial connection or this S1 family of DG2 instantons. Whereas for phi and p, that's for t is 1 over root 5 and the plus sign, so that's going to be here. And so here we see we have an S2 family of DG2 instantons as well as the trivial connection. So this is our main result in picture form. So let me tell you how we prove this and then make some observations. So the proof is very simple. It's just an explicit calculation. We have all the formulae that we need. We can just compute explicitly and check when do we get a DG2 instanton for our ansatz. And it turns out that all you have to do is solve quadratic equations once you set it up correctly. So let's just recall the pictures that we drew for our families of DG2 instantons that we've constructed. And what we observe is that if I look at the plus solutions and the minus solutions, it looks very different. But remember that they define the same metric. They are isometric G2 structures. And so we see that the solution space is actually always different for isometric G2 structures. If you look at the corresponding place for phi t plus and phi t minus, you get a different family of solutions. And similarly, as I already pointed out, if you look at the two different nearly parallel G2 structures that we know, phi TS and phi NP, the only ones that exist in these two families, then again, we have different solution spaces. Here we have an S2 and a point, here we have an S1 and a point. Another observation that I want to make is that although I took the case of the trivial line bundle in the previous theorem, one can also construct examples on non-trivial line bundles, for example, on the Olaf-Wallach space. And the picture that you get is the same, except now you don't have the trivial connection down here, but a non-trivial connection because it's a non-trivial line bundle. An interesting question that you may ask is what happens at t is 1 over root 2? And that's a very interesting story. It's not completely clear, but what actually happens as you hit t is 1 over root 2 is that a whole family of usual G2 instantons appears at this point. So that may have something to do with this special value. And just to emphasize the point, we see that as we increase t, an S2 family of DG2 instantons is born and then dies at t is 1 over root 2. In the phi t plus case, whereas in the phi t minus case, we have simultaneously an S1 family and a 2-point family of DG2 instantons that are born. One of them dies at t is 1 over root 2, whereas the other one lives forever. So next time, I want to talk about the moduli space theory associated with these examples and the Chern-Simons type functional.